Keyword search looks for the same words, but what happens when the words are different and the meaning is the same? For instance, you search, how do I stop my model from memorizing the training data? And the best document says, regularization helps models generalize better. There is almost no word overlap here. But if you know machine learning, you know that these two sentences are clearly related. That is the core idea behind vector search. Instead of searching only by keywords, we search by meaning. And in this video, we are going to build a simple version of that in Python. Hi, welcome back to my channel, and if you're new here, welcome. My name is Anna, and on this channel, I explore machine learning concepts in a simple and intuitive way. If you enjoy this kind of content, consider subscribing and feel free to leave a like and a comment so that more people can see this video. Let's get started. In the previous video, we talked about embeddings, how text can be converted into vectors. In this video, we are going one step further. Once we have those vectors, how do we actually search with them? How do we take a query, compare it with a bunch of documents, and return the most relevant results? That is vector search. And this one idea powers things like semantic search, chat with PDFs, recommendation systems, duplicate detection, and RAG. Traditional keyword search is useful, but it has a very simple limitation. It mostly asks, do the words in the query appear in the document? And sometimes that works perfectly. If I search for gradient descent and the document contains the phrase gradient descent, keyword search can find it, but humans don't always use the same words to describe the same idea. A student might search for cheap laptop, but the product description says affordable notebook. A person might search car won't start, but the help article says engine doesn't turn on. And in machine learning, someone might search, how do I stop my model from memorizing the training data? But the document might talk about regularization, generalization, and overfitting. So the real problem is this. We don't just want documents that share words. We want documents that share meaning. Here is the intuition. Imagine every sentence lives somewhere on a map of meaning. Sentences about similar ideas are close together. Sentences about different ideas are far apart. So a sentence about regularization and a sentence about overfitting should land in the same neighborhood. A sentence about PCA should land somewhere else. A sentence about gradient descent should land in another area. Vector search works by placing both the query and the documents into this space, then asking, which documents are closest to the query? That is really the whole trick. We turn meaning into geometry. Then search becomes a nearest neighbor problem. The query comes in, we compare it with our document vectors, and we return the closest ones. Now let's make this concrete. We are going to build a tiny semantic search system in Python, not a production system, not a vector database yet, just the core idea. We will have a small set of machine learning documents, a user query, and we will rank the documents by meaning. Now let's build a tiny version of vector search in Python. The goal is simple. We have a few machine learning documents, and we want to retrieve the document that best matches a user query. Here are the documents, and here is the query. Notice that the query doesn't use the word overfitting. It doesn't use the word regularization. But as machine learning people, we understand that this question is probably about overfitting. So let's see what happens if we use simple keyword matching first. Here I am doing a very basic keyword overlap. I split the query into words, split each document into words, and count how many words they have in common. This is not a full search engine, but it shows the limitation clearly, and the result is not very useful. The correct answer doesn't strongly stand out, because the query and the document use different words. The query says, memorizing the training data. The document says, reduce overfitting. Same meaning, different wording. That is exactly the kind of problem vector search is designed for. Now we turn the query and the documents into vectors. I already explained embeddings in the previous video, so here we will just use them. Now we compare the query vector with every document vector. And finally, we print the documents from most similar to least similar. Now the result is much better. The top result is about regularization, and that is exactly what we wanted. The search system didn't need the exact same words. It found the document with the closest meaning. The important thing is that vector search doesn't just return one answer. It gives us a ranking. The first result is the most similar, the second result is less similar, the third result result is less similar again. So vector search is basically saying, given this query, these are the documents that are closest in meaning. That ranking is what powers semantic search. If we plot the vectors in 2 dimensions, we can see the idea visually. This is only a simplified view because the real vectors have many more dimensions, but the intuition is useful. And by the way, if you haven't seen my video on PCA, I highly recommend checking it out. So the query lands close to document about regularization. It lands further away from documents about gradient descent, confusion matrix, or dropout. And this is the main idea. Vector search turns search into geometry. Similar meaning becomes nearby points. For 7 documents, the simple Python version is enough. But if we have millions of documents, comparing against every single vector can become too slow. That is when we need vector indexes or vector databases. They help us search through large collections of vectors efficiently. So the concept stays the same. The difference is scale. In this notebook, we build the core idea. In production, a vector database helps us do the same thing with much more data. Now, how are we comparing these vectors? A common method is cosine similarity. The simple intuition is this. We are not mainly asking how far apart the vectors are. We are asking whether they point in a similar direction. If 2 vectors point in the same direction, the cosine similarity is high. If they point in very different directions, the similarity is low. So in our example, the query vector points in a similar direction to the regularization document. That is why it gets a high score. You don't need to memorize the formula right now. The main idea is similar meaning becomes similar direction, and vector search returns the closest matches. For our demo, we only had 7 documents, so we could compare the query with every single document. That is easy. But what if we have 7 million documents or 700 million? At that point, comparing the query against every vector one by one can become too slow. That is where vector databases come in. A vector database stores vectors and make it efficient to search for nearest neighbors at scale. Instead of scanning everything slowly, it uses special indexing techniques to quickly find vectors that are probably close to the query. That is why you hear about tools like Phase, Pinecone, and others. They are useful when our vector search problem becomes large enough that a simple Python script is no longer enough. Once we understand vector search, a lot of modern AI systems start to make more sense. Semantic search is vector search over documents. Chat with PDFs usually starts with vector search over chunks of text. Recommendation systems can use vector search to find similar users, products, songs, or videos. Duplicate detection can use it to find items that are not exactly the same, but are very similar. NRAG systems use vector search to retrieve relevant context before generating an answer. So vector search is not just one tool. It's a basic building block for many AI applications. But vector search is not magic. This is important. A document can be similar to your query but still be wrong, or outdated, or missing the exact detail you need. Vector search can struggle with things like numbers, dates, negation, or very specific constraints. For instance, documents after 2020 and documents before 2020 may sound very similar, but the difference matters a lot. Another big issue is chunking. If we split documents badly, the search system may retrieve incomplete or confusing pieces of text. So vector search is powerful, but it doesn't verify truth. It retrieves likely relevant information. So now we have the key idea. Vector search lets us search by meaning. We take a query, turn it into a vector, compare it with document vectors, and return the closest results. But retrieval alone doesn't answer questions. It only finds relevant context. The next step is to give that context to a language model so it can generate an answer. That is the idea behind RAG, Retrieval Augmented Generation. If you haven't seen my previous videos, I highly recommend checking them out. I cover topics like accuracy, principal component analysis, and linear regression in a similar style. If you found this video helpful, feel free to like it and leave a comment. It really helps more curious minds like yours discover the channel. If you're interested in this kind of content, consider subscribing so you don't miss future videos. As always, all the resources, including the code, will be in the description below. Thanks for watching, and I will see you in the next one. Bye!